Welcome learners, we are looking at the Gaussian elimination method. Okay, now this is the video number 3 wherein we will actually see what is Gaussian elimination method. In the first video we have seen the system of equations. In the second video we have seen what do you mean by the solution, and now in this video we will talk about the Gaussian elimination method. Okay, so let me first put what is Gaussian elimination method. Then we will see one example. Gaussian elimination. In fact, if you remember, in our 10th standard, we have solved the system of equation by elimination, two equations to unknowns. Okay, unknowingly we are using this method itself over there. So Gaussian elimination with back substitution. Okay, there are a few steps. Let me first put up the steps for you. Step 1, write the augmented matrix, of the system of linear equations. As I said, the augmented matrix means to the coefficient matrix A you put the last column as the matrix B. Okay, you put that in one matrix. That matrix is called augmented matrix. Second step, use elementary row operations to rewrite the augmented matrix in row echelon form. Okay, if you reduce the augmented matrix into reduced row echelon form, then it is called Gauss-Jordan elimination method. Okay, but here we will just put that into row echelon form. And third, write the system of linear equations corresponding to the matrix in row echelon form and use back substitution to find the solution. Okay, these are the three steps which we will follow and solve the system of equations. Okay, now again in this method itself we will come to know when we have infinitely many solutions, when we have unique solution, when we have no solution. Okay, so we will solve 3 examples wherein first we will have unique solution, then we will solve for infinitely many solutions and no solutions together. Okay, so as an example, let us take the same system what we have seen. Okay, so let's see how we can convert. We first rub this part. Okay, so as we have seen in the previous part, we have this system of equations. We have 3 equations, 3 unknowns, and we said we can convert. To solve this system of equation is much more simpler than to solve this system. So now we will use Gaussian elimination method to convert this system in this form. how. First, let me take the example first directly, then we will see. We will go back here, the example or problem. Let us put that as solve the following system of equations using Gaussian elimination method. Solve the following system of equations by using Gaussian elimination method. So let me take the same system what we have here, what we have used. Okay, x minus 2y plus 3z equals to 9, minus x plus 3y equals to minus 4, and 2x minus 5y plus 5z is equals to 17. I hope I remember. It was x minus x minus 2y plus 3z equals to 9, minus x plus 3y is equals to minus 4, and 2x minus 5y plus 5z is equals to 70. So this is a system of 3 equations, 3 unknowns. We need to find the solution of this. Okay, so first let us write this system in terms of the matrix form. Okay, the given system can be written in matrix form. Okay, so let us find first what is the coefficient matrix, then the x, y, z, and then this vector b. So for that we have the coefficient matrix to be the coefficient of x here 1, then y minus 2, 3, then we have minus 1, y is 3, there is no z, that means it will be 0, and here 2, minus 5, 5 coefficient matrix. Then we have x, y, z, and on the right hand side, that is matrix B, we have 9, minus 4, 70. Okay, so the given system can be written in this matrix form. Here we have our A to be like this. This is our matrix A, this is our matrix X, and this is our matrix B. So AX is equals to B. A into X is equals to B. Okay, now as we have listed the steps, we have to write the augmented matrix for the system of linear equations. Okay, so as I said, the augmented matrix means you take the coefficient matrix and you add the last column as its matrix B. So here associated augmented matrix is, we take this A, it will be A, and then you put the last column as B here. Okay, that will be, let me write, we will have 1, minus 2, 3, minus 1, 3, 0, and 2, minus 5, 5, and then this B we will keep it here, so 9, minus 4, 17. Okay, if you want to classify them, you can put just a small dotted line here. Okay, now we need to convert this matrix, this augmented matrix, into, we need to convert this augmented matrix to the row echelon form. That means this is our diagonal, below these diagonals all we need to make 0. Okay, we have already seen some examples how to convert the matrix into row echelon form and also reduced row echelon form. Okay, you can go and check those videos there. Now, to make, we have already 1 here, we need to make this 0. So of course 1, and here we have -1, so the operation is you add the first row to the second row. Okay, so now the operation, let me write here operation, our R2 will change to R2 plus R1, we will add it. So if we apply this operation here, we will have this matrix wherein we are not doing anything to the first row and the third row. So let us write the first row and third row as it is. In the color. We have the first row which is 1, -2, 3, 9, and third row also 2, -5, 5, 17 as it is, and our second row changes to second row plus the first row. So -1 plus 1, 0. Here 3, -2, we have 1, 0 plus 3, we have 3, -4 plus 9, we have plus 5. Okay, now from this matrix again we will apply row operations and make this entry 0. So again we have 2 here, we have 1 here, so we will have third row minus 2 times the first row. So our operation will be R3 will change to R3 minus 2 times R1. So we will multiply the first row by 2 and we will subtract that from this third row. Okay, so the operation becomes, we are not doing anything to our first and second row, so let us write first row and second row as it is. 1, -2, 3, 9, 0, 1, 3, 5, and here let me change this. So 2 minus 2 will be 0, then -5 plus 2 into 2, 4, so we have -1, then plus 5 minus 6, again we have -1, 17 minus 18, we have -1, right? Now as the first operation we have done, we have made our first column 1, 0, 0. Now for the second column we already have 1 here, right? We already have 1 here. Now using this one we will make the entries below this 1, 0. So we have -1, we have +1, so the operation naturally becomes, our R3 changes to R3 plus R2. Now remember, don't use R1, because if you use R1 then this becomes non-zero, then your purpose of using these two operations is void, right? So don't use R1 now. Now using these operations our matrix becomes, we are not done anything to our first and second row. So 1, -2, 3, 9, 0, 1, 3, 5, and our third row will change. We are adding the first row, second row and third row. So we have 0 plus 0, 0, -1 plus 1, 0, -1 plus 3, 2, -1 plus 5 is 4. Okay, so again below this one we have made 0. Again we have 1 here. Let us make this one. We have 2 here. Let us make this as 1. And to make this one, what we can do is we can divide throughout the row by 2. That will be our last operation for converting this into row echelon form. So R3 changes to 1 by 2 times R3. So we are multiplying this non-zero, this row by a non-zero constant, non-zero scalar. So again, first row as it is, second row as it is, and third row will change. How it will change? You divide the third row by 2. So it will be 0, 0, 2 upon 2, 1, 4 upon 2, 2. And if you see, this is our row echelon form. Okay, now corresponding to this row echelon form, let us get the required system again. Okay, this is our coefficient matrix, this is our B matrix. So we get the system, we get the system of equations, say, as I said, this is our coefficient matrix. Let me write the matrix here: 1, -2, 3, 0, 1, 3, and 0, 0, 1 into x, y, z is equals to 9, 5, and 2. Okay, when you write this in system form, the equations forms, we have 1 into x, so x, minus 2 into y, so minus 2y plus 3z is equals to 9. 0 into x is 0 plus 1y, so y plus 3 into z, 3z is equals to 5. 0 into x 0 plus 0 into y 0 plus z is equals to 2. So our original system, what we had, this system is converted into our that system, and when you check back, when you go back and check, it will be precisely this one. So as I said in the last examples, solving this system is much more simpler than solving this. So we are converting this into this form by using Gaussian elimination method, Roy-Echelon form. Then we use the back substitution method. Okay, so from this, let me solve this now. So from this implies, let me write equation number 1, 2, 3. From equation 3, we have z equals to 2. Right? From equation number 3, we have z equals to 2. Now substitute z equals to 2. Substitute z equals to 2 in equation 2. Now in this case, when you substitute, it's called back substitution. From here we are going on top. So y plus 3 into 2 is equals to 5. This implies y is equals to 5 minus 6 is equals to minus 1. Okay, and then substitute y is equals to minus 1, z equals to 2 in equation 1. So let me check what is the equation 1. So x minus 2y, so x minus 2 times minus 1 plus 3 times z, 3 times z is equals to 9. And by solving this, you will get x equals to 9 minus 6 minus 2. So we'll have 6 plus 2 is 8, 9 minus 8 is 1. And hence, x equals to 1, y is equals to minus 1, and z equals to 2 is unique solution. Right? We cannot have infinitely many solutions. Finitely many solutions out there. Okay. Now, when you come back here, what will be the other case? When this system has no solution, it will be like when here in the augmented matrix, if you see this augmented matrix during reduction, suppose you have this 0. Suppose you get this 0. So what will have is 0, 0, 0 and some non-zero number here. I repeat, some non-zero number here. In that case, when you write this system, you will have 0 here, right? And in that case, you will have 0 here, and you will write 0 equals to some non-zero number. Okay. In that case, that is not possible anywhere, anytime. That means the system has no solution. Okay. So in the next video, we will see the system when we have no solution and infinitely many solutions. So see you in the next video.